byte of the output. And otherwise, I'll zero extend the carry, zero extend the heads of the two vectors that came in, and add them all together using this plus on word operator. And then I'll split the results of that in two different ways using split 1 and split 2, which will, so split 1 returns the lower order 8 bits, and split 2 here is returning the higher order 1 bits or bit. And then we can take those, take the carry and take the tails of the two inputs and add all those together, and then cons the sum of this lowest order digit onto the front, which stands for the lowest order digit of the output. And finally, the overall add operation is just this thing with the carry argument specialized to being a single 0 bit. Any questions here? Yeah?
When you said that MB to NUT, it looks like you add the bytes at the low end and not at the high end. I mean, it looks like you're shifting the low complete vector to the left and then add the new byte at the low end, but your explanation before was that you added it at the high end. That's confusing.
I might be inconsistent with the way I draw things on the blackboard, but the rubber always hits the road when we look at the Coq code. So this is a little endian representation, which we can reverse engineer from the function that explains what a sequence of digits means. Any other questions? All right, so let's feed this into Coq. I think I won't dwell too much on the details of the proof, but this one might even belong in of a few pretty general bit vector properties that I won't talk about here. Let's just look quickly at the main theorem that shows the correctness of the workhorse recursive function. When we add together a carry bit and two digit sequences and convert that from a digit sequence into a NAT, the result is the same as if we NAT converted each of the three inputs and then just added those together in NAT land, where we know how everything works. So of course this wouldn't look so nice if we were not being sure to avoid overflow. We've allocated the right number of digits, so there shouldn't be any overflow, so there are no scary mod operations showing up on the right hand side here, for instance. And we can do this by induction on the length, and then just point out a few little manipulations. Here I have a multi-byte of length 0. Well, it turns out there's only one multi-byte of length 0. That's the empty list. And I've proved a lemma called shatter vector that will do that for me. So when I pose proof like this, I get a match that checks whether 0 is 0 or not. And you get a different case whether you have a length 0 vector or a length successor vector. And when I simplify everywhere, I've learned that, oh, both of those digit sequences were just empty vectors. And this shrinks down to a pretty straightforward looking thing. And I can use a similar lemma to take a word apart when I know a word has length above 0. And yeah, that's probably about the right level of detail here. There's not too much going on. And we can count on built-in tactics to do most of the arithmetic for us once we unfold the right stuff. So then it's really simple to take that lemma and use it to prove that MB add works correctly, basically showing that conversion to NAT kind of commutes with addition. All right, so what do I do next here? Now we have a functional program that computes words, but this isn't so great if we wanted to compile this into hardware, because there isn't a general compiler from Coq Galena functional programs into hardware. There are many more features in Galena, like recursion, for instance, or data types that aren't finite. We haven't used any of them here, but to expose the fact that we really have followed the rules and we've written hardware compatible code, I'm going to switch to what we'll call a deeply embedded language. I'll fast forward past a bunch of those definitions and bring the language definition on here. So this is a simple syntax tree type that happens to include all the operators that we needed in that example. So what are the operators? Well, first, expr is a dependent type family indexed by the number of bits in the answer that you'd get if you actually ran this expression. Simplest case is a constant, for any number of bits. If you give me an actual literal word with that number of bits, this can be considered an expression with the same bit width. I have combine, which is just for concatenating 2-bit vectors together. So when the inputs have bit widths n1 and n2, the output has width n1 plus n2. And then split 1 and split 2 are kind of the inverses. Collectively, they're an inverse, where if you have an expression whose bit width is a sum, you can pull out either the lower order or the higher order bits and have those as available to you as well. And then I'm building in an add operation, which we will only use in the 9-bit case, though it's for simplicity, it's modeled here in a very general way. And then one of those multi-byte representations, instead of being a vector of words, I'll just make it a vector of expressions, each of which wants to evaluate into an 8-bit result. Any questions on this syntax tree definition? Okay, so now I have here essentially the same code as before, but for instance, instead of calling lowercase c combine in this spot, I call capital C combine. So I'm building a syntax tree where before I was just computing on a data type. But the code is extremely similar. Easiest way to show that, I'll just print mb add prime from before. Just look at this. It lines up 1-to-1, and there's just a lot of capitalization changes and other boring things, like all these constants got wrapped in the const constructor, and really shallow changes like that. So now we have what's called a deep embedding, where we've written this function that when you give it the appropriate arguments, it's going to compute a tree of program syntax. Just down here on this line, we can see mbadd is also defined similarly to before. We just hard code the first argument to the 0-bit. All right. Any questions here?
So now this constructs the syntax tree that does that calculation instead of doing the calculation.
Right. This function, good way to put it. Instead of doing the calculation, this function constructs a syntax tree that, when evaluated, should do the calculation for you. And notice that these inputs here are vectors of expressions themselves. So we'll see how that plays out shortly. To convince ourselves we got that right, we'll need to define what a program means in this language. And I'll do that using an interpretation function that takes in an expression and returns a word of the same bit width. And it's deceptively straightforward looking. It is really the uppercase to lowercase transformation in a sense, where a const we just strip out the constructor and combine and split and add, just switch to the semantic versions instead of the syntactic versions as we go from the left side of the pattern case to the right side. So that's nice and straightforward. And then I can state properties like this one. This is the main correctness theorem for the MB add prime with capital M. I decided to do it by not directly going at semantic correctness. I just want to show, as we saw naively by looking at the two versions of the code, we're generating the same thing as our original semantic function does. So recall, this function with the lowercase m is the semantic version. This one with the capital M is the one that works with syntax trees. So if we ran the syntax generating version on a carry and 2-digit sequences, and then we mapped over the result, which is a sequence of digits, each of which is an expression, and we run each expression. This is the same as evaluating the expressions first and then passing the results off to the semantic version of addition. Because the code mirrors the old version so closely, we don't even need to know what arithmetic is to prove this theorem, which is a nice shortcut. So it's a very short proof script. And that was satisfying to me when I first saw this proof go through. And then we can wrap that into the version for the hard-coded carry bit of 0 or top-level mbadd function, which looks even simpler than the last one. Right. And then, now that we've shown that the syntactic version mirrors the semantic version, we can reuse correctness of the semantic version to get correctness of our new syntactic version, which is basically just, let's watch these steps. I proved that when we have an expression like this one, Okay, so this expression here matches the left-hand side of the purely syntactic theorem we just proved. So I can use this to replace a call to my syntactic function with the semantic version from before. And then this literally matches the correctness theorem for the semantic version. And we have that this expression generator creates correct expressions. Any questions here? All right, well, let's actually run some test cases and see what the outputs of this generator look like. So I'm going to write a function that's parameterized on expressions for 2 digits of one input and 2 digits of another. We're specializing this to 2-digit inputs and therefore 3-digit outputs. And I'm going to run this. I wonder if anyone has any guesses of something we're going to see that we're not going to like in the output. Yeah?
The addition of certain parts which should be computed only once and stored away with a let, and basically computes these things several times.
Right. A key thing about the deeply embedded language we defined is it doesn't have let expressions. In this code up here, I was just using Galena lets, which when we fully execute a run of this function, those all go away, and we get a lot of copy and paste style duplication of expressions, and we can get some sort of superlinear blow up in the size of the circuit, even though it deserves to be linear. And there's one other small thing we'll see that we'll get to fixing by the end. I don't know if it's reasonable to expect anyone to have spotted it here. Let's just run this and see what happens. I'll give this more space. So I think this expression here is duplicated down here, and it's only going to get worse with more digits. There's also one more little thing in this output that makes me not want to call it a day just yet. Do we see any other opportunities for improvement in this expression, even if we manage to get the sharing to be explicit? Anything kind of wasteful that's going on in this expression? Yeah.
I guess the zero thing, the all zero constant is duplicated as well.
Let's see. So I'm not generally going to worry about duplicating constants, though maybe that's worth worrying about. Something related, though. Yeah.
Doesn't do much constant propagation?
Yeah. Look over here. Let's combine together one string of zeros with another string of zeros. This could just be one longer string of zeros to begin with, and then we add that string of zeros to something else. Why would you add 0 to something? We should be able to just short circuit that and cut out the computing the zeros and the addition operation. So by the end of this, we'll get that to happen automatically without complicating the definition of our adder function. Any other questions or comments at this point? I'll just run a slightly larger version too, and we'll see. It doesn't get too much nicer. There's all this. We have 2 combines nested inside this one, or 3. It's like a big tree of these operations that are being repeated over and over again. So we are going to need to add some binders into the language to fix this. So, all right. I'm going to use a technique called parametric higher order abstract syntax to set up a language that has let binders in it. One sort of orthogonal change I'll make as I switch is to start representing the output of add as one big word instead of a list of bytes. And we can easily convert between these two worlds by using this flatten function, which takes a multi-byte of some positive length and turns it into a word whose number of bits is the length times 8 plus 8. And it's a minor miracle that this function type checks. You might think it's a sort of strange way I chose to phrase the type of it. Coq gets angry if I do the more natural thing. And the way this function works is using head and tail operations on vectors and the combine operation on words that we saw before. But we won't need to dwell on the details of this. And I'm going to make a lot of these functions opaque so that Coq doesn't try to unfold them during the proofs. Because remember, we already proved at the top that the semantic version of this operation is correct. So from this point on, we should almost be able to treat all these arithmetic operations as uninterpreted functions and just keep referring back to the correctness proof of the original semantic version. By the way, flatten does what you'd think. If you flatten, then convert to a nat, it's the same as converting the original representation to a nat. All right, so here is a kind of strange looking definition. The P in FOAS stands for parametric, and that's because I'm going to define the syntax of expressions with respect to some unknown type of variables. And the variable is actually a family of types indexed on the number of bits needed to represent this variable. And then we have the 5 constructors from before, whose definitions look exactly the same. And things get interesting. When we get to these last two, there's a constructor to inject a variable into the type of expressions. If you have a variable that needs n bits, this can be treated as an expression that needs n bits. And then the most interesting case, the let-in constructor, this is what we'll need to use to express sharing. It's parameterized over 2 bit widths. It takes in one expression of 1 bit width. This is the expression that's getting a new name assigned for it. And then the body of the let is a function from a variable of exactly as many bits as this thing generates to a new expression of the overall number of bits that the final answer should have, as we see by having that number copied over here. And then the final trick to create what's called an adequate representation of expressions is to say, in the end, what is an expression? It's a polymorphic function where you tell it what variables should be, and then it tells you a syntax tree that adopts that choice. So I think this is a good point for me to, I'll show one more definition, and then I'll bring the blackboard back into play and work through an example that might show why this makes any sense to parameterize over a type of variables like this. Do note that if I put expr in this position instead of variable, Calc would not be happy. Does anyone know why not? Yeah.
In inductive types, all the recursive occurrences have to appear in positive positions.
Right. This would be a negative position for a recursive occurrence of the type expr, and Calc would rightly reject that definition, because if it were accepted, we could then start writing non-terminating programs. We could easily encode the syntax of lambda calculus and an interpreter for general untyped lambda calculus. So it makes sense that that's not allowed. And it's kind of interesting with this small change of treating variables differently from expressions. Suddenly everything terminates, and we can prove all the theorems we want. So let's see an example of this in action. Well, first, I want to show, again, I can write the same program as before, but it's in the new syntax. It looks pretty similar, except now I have the let-in constructor instead of the built-in let of Galena. And most of the rest of it is the same. Notice how we're nesting all these anonymous functions to bring into scope names for all the things we're let binding. And they all get dropped into appropriate positions using the var constructor to mark every spot where we use a let bound thing. Before, we just mentioned, say, carry9 directly without a special injection. But modulo those shallow differences, it's the same code as before. And all right, I still want to prove it's correct. I'll need a semantics for this language again to let me do that. So I'll write this little interpreter. And this is going to be probably a deceptively simple looking interpreter. And then I'll work through an example execution trace on the board, and we can see why this and how this is using the flexibility of parameterizing over a variable representation. So interp is polymorphic in the bit width of the expression. The weird thing that happened here is I'm saying, please give me an expression where you represent variables as words, where words are exactly what I'm looking to get out in the end. And what that lets us do is the constant case and the variable case are exactly the same, because I've effectively said variables should be constants. Then it's very easy to evaluate expressions. And combine and split and add look just like before. The let-in case has a little bit of a twist to it. We interpret the expression we're giving a name to, and then we pass that as an argument to the body. Recall the body of a let-in is a function from a variable standing for the new thing we created into an expression for the body. So we take the interpretation of the thing we're defining, and we pass it in as an input into the body E2, and then go on and interpret that. And then in the end, we can take an